So my name is Elizah, and I'll be presenting today my research study that I did this summer with my mentor, Dr. Elizah, entitled An In Silico Recreation of the PCR-RFLP method for Typha species identification. So the agenda for today, I'll just show you a quick overview of what to expect in my presentation. I'll be presenting to you my introduction, my methods, results, and discussion, and lastly, my conclusion and future initiatives. So just to give a quick background on Typha species, they are a perennial aquatic herb from the Typhaceae family, and they're abundant in wetland ecosystems. So when we look at these two pictures here, just by looking at them, they're kind of hard to differentiate. So to really identify between these two species, we can look at their morphological characteristics by comparing their leaf widths and the position of their staminate and pistillate. So in Typha here on the left side, more commonly known as the broadleaf cattail, their leaf widths can reach up to an inch wide, and the position of the staminate and the pistillate heads are close together, if you can see. And on the right side, which is the Typha angustifolia, more commonly known as the narrowleaf cattail, has a leaf width that can reach up to half an inch wide, and these staminate and pistillate heads are approximately separated by 3 centimeters. So distinguishing these two types of species by their morphological characteristics alone is unreliable because it can be affected by direct environmental alteration, genetic variation, and developmental change, as well as by looking at their staminate and pistillate is also pretty difficult, since after their reproductive season, the staminate head dies and falls off. So field identification will be pretty difficult after their reproductive season, which is why molecular genotyping would be necessary for a species identification. So in previous studies conducted by Lam and Drennan, they used DNA barcoding to potentially differentiate T. latifolia and T. angustifolia, as well as the hybrid TX glauca, which is a cross between these two parent species. So DNA barcoding uses short DNA sequences amplified using PCR from a defined region of the genome. These genetic barcodes can allow species-level identification. Although DNA barcoding is a valuable technique for species identification, it can get pretty costly. So I'll be proposing to use a technique called the polymerase chain reaction restriction fragment length polymorphism, short for PCR-RFLP. And this method involves obtaining DNA amplicons through PCR, followed by the digestion of the DNA amplicons through RFLP with its appropriate restriction enzyme that results in unique DNA fragments used for species identification. This is an efficient method for species identification because it is simple, reliable, and inexpensive. So why is distinguishing between cattail species important? They're important for understanding a wetlands habitat. In a recent study, samples of T. latifolia collected around ponds at risk for metal contamination revealed that the roots of T. latifolia contained high accumulation of metal, which can be used as a potential bioindicator for heavy metal water contamination. Additionally, T. angustifolia can tolerate slightly saline water, while T. latifolia cannot tolerate any amount of salinity. It's also important in the conservation standpoint from where the Typha species grow. TX glauca, which is the hybrid species between T. angustifolia and T. latifolia, shows more invasive characteristics and can live in a wide range of environmental areas. So for my methods, we had to identify SNPs, and then we went through sequence analysis. So 2 cattail species samples, T. latifolia and T. angustifolia, collected around Worcester County, Massachusetts. The samples went through DNA barcoding of the RBCL and MATK gene sequences from a study conducted by Lam and Brennan. Putative SNPs were then identified when the aligned sequences were identical, except at the location of the differing nuclei. So next is like the in silico sequence analysis. So we use NebCutter, which is a restriction analysis tool, to find restriction enzymes of the sequences where the putative SNP was located. The restriction enzymes were chosen for RFLP analysis at Worcester State University based on the result of the theoretical digest performed on Rebase, which is also like another bioinformatics tool. These restriction enzymes were selected based on 2 criteria. One, they had to show the theoretical digest had to show a distinct and consistent DNA fragment of the species with its appropriate restriction enzyme at the SNP, but a completely different pattern on the other species. So moving on to my results and discussion. So in figures 1 and 2, we can see that five putative SNPs were identified after the alignment of DNA barcode sequences from the cattail species collected around Worcester County. The sequences were obtained from PCR fragments amplified using primers to different sections of the RBCL gene, which is commonly used in DNA barcoding. In the first figure, this sequence was taken from Lam and Brennan study, and the figure for primer 1 in figure 1, and for figure 2 is the sequence alignment for primer 2. Yeah. So these SNPs of the RBCL PCR amplicons were analyzed on NebCutter, and table 1 and 2 shows the results for that. We have restriction enzyme ALU1 and ACI1 for primer 1, and ALU1, ACI1, and CVIQ1 for table 2, which is from primer 2. And these were used for a theoretical digest of PCR, where these restriction enzymes were chosen for a theoretical digest of PCR amplifications of the RBCL gene. So as these restriction enzymes were likely to cut the amplicons at multiple locations, theoretical digests using Rebase produced distinct DNA fragment markers in both sample species. The theoretical digests were separated using 0.7 agarose gel. And in here for figure 3 at the left side, we have T. angustifolia and T. latifolia with their appropriate restriction enzyme. And at the right side, we have T. latifolia in ALU1 and T. angustifolia with ACI1. So we basically just switched the species with in respect to the restriction enzyme. And for figure 4, here at the left side, we have the theoretical digests of Typha species with their appropriate restriction enzymes. And on the right side with the species if they're not appropriate restriction enzyme. So the different banding patterns acquired from the digestion of the Angustifolia and T. latifolia can be used as markers for reliable species-specific identification without any need for costly nucleotide sequencing. So ultimately, the purpose of this study was to provide a reliable and rapid approach to identifying cattle species that have an unreliable morphological basis of classification. So in conclusion, this study proposes to use a simple and reliable technique for Typha species identification, restriction enzymes ALU1, ACI1, and CBIQ1 were used to identify T. latifolia and T. angustifolia. I also forgot to mention this, but the results of this study is in the process of being validated at Worcester State University, since everything that I did was theoretical. And future studies should include more type of sample species as well as hybrid species such as TX glauca. And final remarks, I'd like to say thank you to Talaria for making this possible. This is actually like my first scientific research, like doing it independently. And I also like to thank my mentor, who was very nice and accommodating, and who was always there when I needed additional help. And yeah, thank you.